regular lecture. Today is our last regular lecture. Next time, review for the final. So this part, I want to complete the heap sort, but I will skip the analysis part. I only describe the idea of the heap sort. Yeah. So analysis part, it takes a lot of time, so I just skip it. Yeah. All right. And this part will appear in our last quiz. Okay. Yeah. No computation question from this part. Yeah. Because we do not have chance to practice computation questions. Yeah. So I skipped that part. But concept questions will appear in quiz, our last quiz, quiz 6. That's also the part A of our final. Okay, yeah. Yeah. All right. Some of the questions from this part, but we also need to have some questions from Module 4. Yeah. Okay, for quiz 6, yeah. Because it's part of final. Yeah. After midterm, yeah. Content after midterm. Yeah. All right. So the final 1 week from Thursday. Okay. Yeah. Just remind you another time. 1 week from Thursday. Yeah. All right. Yeah. Yeah. All right, so let's start. 8.1, Introduction to Heapsort. Yeah. All right. This is our sort number 6. Yeah. So in this one, we need to do things different. Yeah. So what is the main focus here? There are some special requirements. Yeah. So when we design this sort algorithm, we need to consider some special requirements. The first one, we want to control. The worst case efficiency is big theta of n log n. Yeah. That means we want to avoid the bottleneck. Yeah, bottleneck. Yeah. All right. Yeah. Because some of the sorts, their worst case very slow. Their worst case in big theta of n squared. Okay. Yeah. That's the bottleneck. Okay. Yeah. So due to some reason here, we want our worst case still in this big theta of n log n. Yeah, so that's the first requirement. Merge sort satisfies this requirement. Okay? Yeah. Merge sort. Yeah. All right. Number 2, in place. Yes. So here, let me explain this in place. Yeah. So in the quick sort, yeah. Yeah. I didn't have a chance to explain this in-place sort. Yeah. So this in-place algorithm, okay? What's that? We learned in-place elements before, right? The elements are in place. Yeah. So you know the meaning. Yeah. But here, in place means the algorithm is in place. It's different. Different from the meaning elements are in place. Yeah. So the meaning, the algorithm in place means the extra space used in big theta of 1. That's the meaning of in place. Okay. The extra space I explained last time. The space used other than input output. Yeah. Input output, that's the normal use. normal space use. So we do not count it. Yeah. So other than input output, you may need to use extra space. Yeah. But an in-place algorithm means you control the extra space and put it under this control, big theta of 1. Yeah. Because if we do not use a lot of space in this extra part, we can make our algorithm faster. So it's another reasonable consideration, number 2. Yeah. Number 3, maintain dynamic data efficiently. Yeah, so that's something new for this one. Dynamic data. Because when you work on your data, the data keeps changing, right? Yeah. You keep adding new data items, or you delete some of the items. Yeah. So when you do insertion, deletion operation, you need to maintain certain structure. Yeah. There is some structure, special structure on your data. Yeah. Yeah. But when you do deletion, insertion, you may change the structure. So you have to recover the structure. Yeah. So this requirement number 3. So you need to do some special operations. Yeah. All right. So that's the 3 special requirements for this new algorithm. When you design this new algorithm, you need to, make sure you satisfy these 3 important requirements. Yeah. All right. Yeah. Yeah. All right. Yeah. So here, efficiently, right? Yeah. So here, when talk about efficiency, efficient. So what do you mean efficiently? Yeah, remember? Yeah. So I remember I mentioned sometime before, right? Yeah. Yeah. Because when we do insertion, yeah, let's record this insertion operation. When we do insertion operation, we have linear insertion and binary insertion, right? Yeah. Yeah. So linear insertion and binary insertion. For linear insertion, the efficiency is big theta of n. The binary insertion, its efficiency is big theta of log n. Okay? Yeah. And when we say efficiently, we mean we want the efficiency of this binary insertion, not the linear insertion. Okay? The binary insertion, binary type insertion. Yeah. Yeah. So yeah. So that's not easy. Okay? All right. Yeah. Then idea. So now we need to get an idea. And the title of this module 5, we call it Advanced Data Structure. So here we need to do some design work at a data structure. Yeah. So usually in our algorithms, sometimes when we consider some advanced algorithms, usually advanced algorithms may rely on advanced data structures. Yeah. So here it's an example. Yeah. Here, because we need to do something special. Yeah. So we need to build some special structure to organize our data. Yeah. Especially in order to get this requirement number 3. Yeah. All right, so let's look at the data structure, the properties of the data structure. First, the data structure should have a binary tree structure. Yeah. Why? Because we want the binary insertion, right? Yeah. Yeah. When we insert a new element into our data structure, we want to have the big theta of log n. If you have a binary tree, then you can get that easily, right? A binary tree structure. So when you do the insertion, you do the navigation level by level, okay? Yeah. So when you reach the bottom, you need to do this many comparisons. Yeah. All right? Yeah. Design of data structure. Yeah. So when we design our data structure, we want to make our data structure as simple as possible. Yeah. Not too complicated. Because people don't like complicated structures. Yeah. All right. So let's look at the candidates. Yeah. So in our basic data structure candidates, yeah. So let's see which one we like to take. Yeah. All right. Array is a candidate, right? Yeah. So we like to use array, yeah, because it's so simple. Yeah. Yeah. Very easy to use. Array is the first candidate. The second candidate, linked list. Yes, linked list. So you learned the linked list before, right? In your data structure course. Yeah. So for the linked list, why we think about this linked list? Because we need to store a binary tree, right? When we store a tree, we need to consider parent-child relationship among the nodes, right? Yeah, yeah. So your binary tree, there are many nodes in the tree, okay? How to specify the parent-child relationship? Yeah. Linked list allow you, okay, specify the left child, right child, and the parent, right? Yeah, 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 yeah. So you get, yeah. Each node you can create a pointer, right? Yeah, point to left child, point to right child, then point to parent node, right? Yeah. Things like that. Yeah. So we have two candidates we can consider. Yeah. All right. Yeah. Yeah. Definitely, array is much easier than linked list, right? Linked list is too complicated. Yeah. People like to avoid it. Yeah. If you can avoid it, so then we will try our best to avoid it. Yeah. We don't want to use linked list. Yeah. But the question is it possible to use array to store a binary tree? That's the question. If you can use array to store
the hashed indices.
You do not need a hash because array automatically it has the natural indices, right? Yeah.
Oh yeah.
Array has, yeah. So you don't need a hash. Okay.
Okay, but there's automatically a hashing implementation that allows the array to be possible within that programmatic context.
Yeah. Yes. No hashing needed. Yeah. Because otherwise you make it more complicated. Yeah. So you don't want to do those complicated things. Yeah. All right. Yeah. Now the question, because when you use array, you cannot use any pointers, right? Yeah. But the good thing is we don't like pointers. Yeah. Yeah. Most people they don't like pointers. Yeah. So we want to avoid pointers. Yeah. So when we use array, we can only manage indices. The indices we can use to control elements. Yeah. Yeah. But the question is it enough to just use indices to specify the structure of a binary tree? Okay. Yeah. If using array indices, it's enough. We can define parent-child relationship using array indices. Then it's good enough. Okay? Then we solve the technical problem. Then we can store a binary tree inside an array. Yeah. So next we need to solve this technical problem. Yeah. All right. Yeah. Yeah. So now we want to think about how to store a binary tree inside an array. And we need to define the way to specify parent-child relationship. All right, yeah. The next, yeah. So here I already explained the efficiency. All right, yeah. So now let's consider. We need to do some work on an array. Yeah. Yeah. All right. We need to do some special work on an array. Yeah. All right. Yeah. So here, this place, I want to explain the efficiency part. Yeah, we already did the efficiency part. So the insertion, right? So here, let me skip. Yeah, because we already talked about. We want to use this way. Yeah. Oh, all right. Yeah. So insertion part, we pass it. Yeah. Let's save some time. Okay. All right. Let's move to the next step. Underlying data holder array, but how to build a binary tree structure inside an array. That's our next step. All right. Yeah. We want to find an easy way to define parent-child relationship. If we can do it, then we can use array directly. Yeah. All right. 8.2, binary tree structure in an array. All right. Yeah. How to build? Yeah. So here we need to use a heap data structure. Yeah. We need to define this special data structure called a heap. Yeah. So what's the definition of it? Yeah. The properties we need. For a heap, the underlying storage structure still array, but we need some more structure properties. First, it should be near complete binary tree. Near complete. Not complete, near complete. Because if you say complete binary tree, then there is a limitation on the number of nodes, right? Yeah. Because in that situation, n must be power of 2 minus 1. If you have this many nodes, then you can have a full, complete binary tree. Yeah. But in general, we don't have this form for our n, the data size number. Yeah. So for the general case, the best you can do, near complete. Yeah. Why? Yeah. So here, another reason why we want to make it as close to a binary, as close to a complete binary tree as possible, because the complete binary tree is the most balanced binary tree, right? Balanced. Yeah. So here we want to get a, most balanced binary tree. Okay? Yeah. If it is balanced, then when we do the navigation through this tree, then we avoid the worst case, right? Yeah? Because the best case, when you go from the top node, the root, to the bottom, you only need log n steps, right? Log n step. So that's our requirement number 3, right? When you do an insertion, you need a big theta of log n. Okay? So when you have a complete binary tree, you can make it happen. Okay? Yeah, but here, we cannot achieve complete binary tree in general, but the next best thing, near complete. Yeah. So what do you mean near complete, right? You need to give a specific meaning for near complete. Yeah. The meaning is like this. Yeah. When you draw here, you draw a binary tree, okay, like this. Yeah. This is a near complete binary tree. Why? Yeah. Because only the bottom level is not full, right? Yeah. Yeah. This bottom level, you know, there are some missing nodes, right? Yeah. There are some missing nodes. Yeah. So the bottom level of this binary tree may not be full, but other than this level, all the levels above the bottom level, all full. Okay? No missing node. Yeah. So that's what we call near complete binary tree. Yeah. And in this one, yeah, also very balanced. Yeah. So if you go from top to bottom, yeah, you can still get log base 2 of n number of comparison approximately. Okay? Yeah? So that's our, the property we want to have. Yeah. Near complete binary tree. All right. Yeah. Then the third one, yeah, another, remember we want to maintain dynamic data. So we need to manage our space, yeah, because array, if we want to use array, the array has some properties, right? Array, after you define an array, the size is fixed, right? Yeah. After you construct an array, then we know array is an object, right? Array is an object. After you construct an array object, you cannot change its size. Okay? Yeah. If you want to change its size, you can only create a new array, then copy your data from old array to new array, then you destroy old array. If you really want to change the size of your array, yeah? But you cannot grow your old array. Okay? You are not allowed to change the size of your old array. That's the property of an array. Yeah. So then, how to store data dynamically in your array? Because storing data dynamically, it means you need to keep adding new data items, right? Yeah. Sooner or later, you run out of capacity, right? Yeah. You reach the capacity. You have to, after your array is full, you need to insert a new element, right? Yeah. So you need to consider that part. Sufficient space for dynamic data. Yeah. All right. Yeah. So here you can see you need to solve many small technical problems. Yeah. All right. Then certain relationship among nodes. Yeah. So when you define parent-child relationship, yeah. All right. How much space is sufficient? Yeah. So here we need to answer the question. Yeah. Because the sufficient space to that technical question may not be easy to solve, right? Yeah, yeah. Sufficient space. How do you make your space sufficient? If at the beginning you allocate certain amount of space to your array at the beginning, sooner or later you run out of your space. You have to increase the size of your array. Yeah, right? Yeah. Yeah. All right. Yeah, quite annoying. So let me mute my phone a little bit. Yeah. All right. Okay. All right. Okay, good. Yeah. All right. Yeah. So the space sufficiency, we need to solve that technical problem. How to manage our array so that when we grow, when we increase or decrease the size of the array, we can handle. Yeah. Gracefully. We can handle the size of the array gracefully. Okay? Not in a nasty way. Right? Now, what's the nasty way? Let me describe the nasty way. All right. Yeah. Yeah. That idea also very interesting. Okay. Yeah. All right. Make array space sufficient for dynamic data. Yeah. Yeah. Because you cannot make good prediction at the beginning how much space you need for your array, right? Yeah. Yeah. So at the beginning, yeah, you do not want to allocate too much space to your array. Yeah. Yeah. Otherwise, most of the time, a lot of space of your array is unused. That is not efficient, right? Yeah. Yeah. So at the beginning, you want to allocate relatively small array to store the data. Yeah. But at some time, you need to grow. You need to change the size of your array. Yeah. But the question is, remember, you cannot change the size of an array directly. So you have to do some copy work. Array data copy work. Yeah. When you do data copy from one array to another array, it takes time, right? Yeah. Especially when the array size is very large, it takes time. Yeah. So you need to consider that problem. Yeah. All right. So let's look at the whole picture. Yeah. At the beginning, we assign certain amount of space to an array initially. Okay? Yeah. All right. Keep adding data and monitoring the size closely. Yeah. When you fill the capacity of the array, yeah, you need to think about do the data copy from this array to a new larger array. You need to create a larger new array. Then you make data copy from old one to new one to get more space. Right? Yeah. When a threshold, yeah, you need to set some threshold. Threshold, yeah. Because let's say 90%. Yeah. Yeah. So you can 90% of the capacity. Okay? Yeah. For example. Okay? Yeah. Yeah. When you reach that 90% line of the capacity, then you need to do some preparation work. Yeah. Do preparation, yeah, for the data copy. Okay? All right. Yeah. When you reach the 100%, yeah, hopefully, yeah, you have very good preparation. You have your array transition almost ready. That's the ideal case. Yeah. All right. Usually it is very expensive to copy a large array. Think about, suppose your array contains millions of data items. Pretty large, millions of data items. But when you copy that large array from one to another, it may take a lot of time, okay? Relatively a long time. So here, what I mean, if it takes several seconds, we treat it as a long time, right? Yeah, because in our waiting time, when you need to wait a few seconds, that's too long, right? Yeah, yeah. People cannot tolerate. Yeah, yeah. Even 3 seconds, that's too long. Think about it. When you do your work, occasionally you need to wait, you need to pause 3 seconds. That's too bad, right? Yeah. So we don't want that to happen. Yeah. So that's why I said, when we make data copy, we want to do it gracefully. Yeah. Waiting 3 seconds, that's not gracefully. Okay? Yeah. All right. All right. So we don't want our users notice the delay for the data copy. Yeah. How to make that happen? Yeah. Then you need to do something very smart. Yeah. Here I can describe some idea. All right. Here I draw a diagram. This peak time, yeah, I mean data copy. Yeah. Yeah, because when you do the data copy, it consumes a lot of CPU power. Okay? Yeah. Most of the CPU power goes there to do the, millions of data copy. Yeah. Okay? Yeah. Then your users need to wait, right, during this period. Yeah. So the most CPU power does that data copy. So people need to wait for the CPU power coming back, right? Yeah. All right. So, yeah, we want to avoid this peak CPU power consumption situation. Yeah. But how do we level out this peak CPU consumption? Yeah. Yeah. We want to spread the CPU consumption in this flat way. Flat way, okay? Yeah, no peak, yeah. And the waiting time, yeah, so, the height, yeah, that's the waiting time, not too long, okay? Yeah. Several milliseconds, let's say, several milliseconds. Then people won't notice that, right? People won't notice the difference. Waiting milliseconds. Okay? Yeah? Yeah. How to make that happen? Yeah. Here, let me describe, some smart idea. Yeah, very simple, not hard. Yeah. All right. Yeah. Let's say, when we reach the 90% of line, yeah, yeah, because so this is the whole array. Okay, yeah. So we draw that 90% line. So this is the 90% line. Okay. When the array is filled and it reaches this 90% of the capacity line, then we need to start to do the data copy from old array to new array. Okay, all right. The new array double the array size. Double the array size. Yeah. Okay, so we have plenty of space. Double the size of the old array. All right. Then, when we do the data copy, when a new element inserted, one element inserted, okay, then you copy 10 old, 10 old data item. How about that? 10 old data items. Yeah. Every time one data item inserted, yeah, then you copy 10 old data items from old array to your new array, newly created array. But when you copy 10 data items, you do not need a lot of time, right? Yeah. So you can think about you only need milliseconds, a few milliseconds, you make that 10 data item copy, right? Yeah, very fast. Another new inserted, another 10 copied. Okay. But after you get the remaining 10%, you do 10 times copy, you copy all 100% to the new array, right? Yeah. All 100% elements to the new array. Think about that. Okay? Yeah. Yeah. In that way, yeah, no relatively long waiting time, right? Yeah. So that's the graceful way to make your data copy. Yeah. Yeah. All right. Yeah. So then we move to the next step. Yeah. So we solve that technical problem. Okay. All right. Next time, heap property. Yeah. This time, yeah, we haven't defined parent-child relationship. So we need to do that first. Yeah. Relationship among heap nodes. Yeah. Yeah. All right. Yeah. So when we store binary tree, then how to tell if we consider two elements in the array, how to tell if they have the parent-child relationship. Yeah. All right. Yeah. So we use the indices of the elements to define parent-child relationship. Okay. Yeah. All right. Yeah. Now, let me use a diagram, simple diagram to explain the parent-child relationship. Yeah. P colon I, yeah, let us assume the index for P node, parent node, is I. Yeah. Then the left child, right child will make this definition. The element with 2i, we double the index of the parent node, then we make the node for the left child of P. Yeah. Then the right child node index of 2i plus 1. Yeah. We make that node as the right child node of P. Then we can easily implement this definition, right? Yeah. Very easy to implement. Yeah. No pointer is needed. Yeah. Yeah, because we use the math formulas to do the definition, to get around the pointers here. Yeah. All right. But when you define in this way, so there is one little thing you need to consider. So here, you cannot use the index of 0, because when you double it, the same node, right? Double 0, still 0. Yeah. You want your child node different from your parent node. So you need to skip the first node with index 0. Yeah. Then for all other elements, you're fine. Yeah. So when you double it, you get a different element. Yeah. All right. Yeah. Relationship among heap nodes. Yeah. Now, so let's study some details of the heap. Two types of heaps. Heaps. Max heaps. First type, max heap. Second, min heaps. All right. Yeah. Because for the max heap, we need to define this property, max heap property. What's that? The value in the parent node, A of I, value of parent node is greater or equal to each of its child node. That's max heap. Parent node has larger values than their child nodes. But sometimes we may need the opposite way, right? Parent node has less values than their child nodes. That's the min heaps. But they have similar structures. So here we only need to consider max heap. Min heap, we just do some symmetric operation. We can get everything from max heap to min heap. All right. So then, why we need to define max heap property, min heap property? Because we need to do the sorting, right? When you do the sorting, you need to maintain some order information in your heap. So max heap property, we want to maintain the max heap property in our heap. Then we can do the heap sort. If you do not have the max heap property, then you cannot run the heap sort. All right. Next, let's look at a max heap example. Here, look at this is a max heap. Everywhere you can check the max heap property. Here, let me draw. Look at the local triangle. So here there is no right child node. So it's the value of parent node greater than the value of left child node. Look at this local triangle. The max heap property is satisfied. Then look at another local triangle. The max heap property is satisfied. Then this local triangle, max heap property is satisfied. The last local triangle, max heap property is satisfied. Now you can say the max heap property is satisfied everywhere. Then we get a max heap. After you have a max heap, then you can run heap sort. So we need to build a max heap first. Then we can do heap sort on a max heap. To maintain the dynamic data, so you may get a new data come in, then you insert it somewhere. After the insertion, you may break the structure. You may break the max heap structure. Then you need to fix it. You need to fix the max heap structure. But the fix operation, you can use big theta of log n to fix it. Fix the structure violation. All right. Here. How to store this near complete binary tree in an array? It's very easy. Okay, we skip the first location at index 0. The first node we store here. Then it's two child nodes, left child, right child, at the node position index 2 and 3. Then the two childs of node 2 at position 2, then you have two elements at 4 and 5. Okay? Yeah. So you keep arrange your elements in this way, you can see the whole binary tree corresponding a max heap can be stored in the array without any problem. Okay? Yeah? Yeah. No pointer needed. You can store that near complete binary tree easily. Yeah. So we do not need a linked list, yeah, to address parent-child relationship. Yeah. All right. Maintaining the heap property. Yeah. When you have a violation, how to recover the max heap structure. So maintaining the heap property. Yeah. All right. How to fix it? How much work do you need to fix it? Yeah. Let me explain that. Yeah. If there is a violation in this local triangle, yeah, that means the max heap property is not satisfied. Then we need to apply the swap operation to recover the max heap property. Yeah. All right. How to do it? Yeah. All right. So then, let's assume there is a violation. Yeah. All right. Yeah. Yeah. And yeah, we only do local fix here. The global fix. Yeah. So after we make the local fix, then we consider the global fix. Yeah. All right. Yeah. So we assume we have a max heap at the left subtree, another max heap at the right subtree. Then let's do the local fix. Yeah. For the local fixing operation, yeah, yeah. After that, you need to check for the global violation. Yeah. Make the global fix later. Yeah. Let's look at the local heapify operation. Yeah. It's a recursion approach. Yeah. All right. Yeah. Now, look at the pseudocode. Yeah. Let's compare the value of parent node A of I and A of 2i. If A of I less than A of 2i, one violation, right? Yeah. Yeah. So let's do the preparation. Yeah. All right. So we use a temporary variable we call the largest to store the larger, the node with larger value 2i. 2i. Yeah, A of 2i has larger value than A of I. So let us store 2i in this temporary variable largest. All right. Else means A of I greater or equal to A of 2i. Then, because the value in index I is larger, so we store I in this temporary variable. Yeah. So that's the first case. The second case, we need to consider the relation between parent and the right child node. Yeah. All right. Now, let's compare. A of largest, this time, yeah, yeah, we need to use A of largest. Yeah. The larger one in the previous two nodes. A of I, A of 2i. Yeah. So A of largest. If it is less than A of 2i plus 1, then we update this temporary variable. Largest equals 2i plus 1. Otherwise, we do not need to do anything, right? We use the older value in the largest. All right. Then, after that, after you you get the index of the largest value among the 3 triangle nodes in this temporary largest variable. Last step, you need to do the update. But when you do the update, you need to check if the value in it equals I or not. If equals I, no update, right? Yeah. Because no violation. If the largest equals I, there is no violation. So you should not do anything. Yeah. But if not, not equal, then you have to fix it. Yeah. You swap. You do the swap operation between A of largest and the parent node A of I. After it, you fix the problem locally. It's a local fix, but not a global fix. Yeah. The global fix, we can use multiple local fix to get a global fix. Yeah. How to do that? Yeah. Here, let me use a simple example to show you how to use multiple local fix operations to do global fixing operation. Yeah. A max heapify example, simple max heapify example. Suppose this is a heap, yeah, but there is a violation. Here I use this gray color to show you there is a violation in this local triangle. Yeah. Value for smaller than each of the value of each of the child nodes. Okay, child node. Yeah. So you need to fix it. Yeah. You need to run the local heapify operation to fix it. All right. Yeah. So, all right. Then, by the pseudocode, the algorithm in the previous slide, we swap these two. Yeah. So we fix, you can see we fixed this local triangle, right? We recover the max heap property in the original local triangle, but this node is still dirty. Okay? Yeah. So we use gray color to mark a node with potential violation. Potential violation. Yeah. So we can call it a dirty node. It's not clean. Okay? Yeah. Violation there. Then you consider this local triangle, there is a violation, right? Yeah. So you need to do swap between these two nodes. So after another swap, then the original dirty node reaches the bottom, then no violation anymore, right? After the dirty node reaches the bottom, violation is gone. Yeah. So it becomes a clean node. Yeah. Yeah. So then you get a whole max heap. Okay. Here you can see, you just keep track of the dirty node. Yeah. Any place a dirty node goes, you may have a violation. You need to check the max heap property. And if you detect some violation in the current local triangle, you need to run the local heapify operation to fix it. Then you need to keep track of that dirty node to another level down. Another local checking and fixing. Okay? Until you reach the bottom. Or when you do the detection, there is no violation, then you can stop. Okay? All right? Yeah. So in this way, you can do the global fixing operation. Yeah. All right? Yeah. Yeah. Then building a heap. Yeah. So after that, you need to build a heap. Yeah. All right. Yeah. See, because I do not have this much time. Yeah. To build a heap. Yeah. So I may like to, get out. Yeah. I may like to describe the idea to complete the heap sort. Yeah. All right. Actually, the build operation. Yeah. So let me do quickly. Yeah. So given random array, first we just arrange all the elements. Then we run the heapify operation. Okay. Yeah. Triangle by triangle. Okay. Yeah. Bottom up, all the way bottom up. Okay. Then do the fixing. Okay. Global fixing. Remember. Yeah. Triangle by triangle, bottom up, following certain order. Then, yeah. So here I run this example quickly. Yeah. I just tell you what to do. Okay. Yeah. Then, after we build a max heap, yeah. Okay. So we are at the stage we need to do the heap sort. So the last 5 minutes I want to describe the heap sort. Okay. Yeah. So I quickly go through the building the heap. Yeah. All right. Bottom up way. Yeah. So you can, study my example carefully. Yeah. All right. So here I just jump to the heap sort topic quickly. Yeah. All right. Let me quit this slide and jump to the last topic. All right. Last topic, we will do the heap sort. Okay. All right. Yeah. Oh, yeah. Oh, sorry. Oh, here. Yeah. This one, this heap sort. Yeah. We do not do analysis. I just give you the idea of heap sort. Because it's pretty simple, so I can complete it in 5 minutes. All right? Yeah. All right. Before we run the heap sort, yeah, here we assume we already have a max heap. Okay? Yeah. Because we run our max heapify operations. Okay? We build a heap. When we build a heap, we also run max heapify operation, right? So you can see. We use max heap operation, we can get a max heap before we run the heap sort. Now, let's run the heap sort. All right. After you have a max heap, is the largest element at the root of the max heap? Based on the max heap property, right? Largest element must be at the root. When you know the largest element at the root, do you know you can put this element in place immediately, right? You know when the array is sorted, the maximum element is at the end, right? Yeah. So now you can use one swap operation to put the max element in place immediately. One swap, right? Yeah. So this max heap operation, what swap? You do swap, yeah, because the root corresponds to location at index 1. Okay? All right. And the final location in place, its destination location, the last location, right? Yeah. So you just do one swap operation between these two elements, swap. You put one element in place. After you put one element in place, can you eliminate that in place element from consideration? And you look at the remaining heap, right? The remaining heap may not, after that swap, it may not be a max heap anymore, right? But you can run max heapify operation to recover to max heap. All right? So recover the heap structure. You know how to do it. Max heapify, okay? Yeah. But after that, can you put another element in place? Because the root element of the current max heap you can put it in place by another swap operation, right? Yeah. So now the procedure, you do iteration. Okay, all right. First, you build a max heap first. Yeah. Here, I tell you, the building cost is big theta of n. So we skip that part. That part, we need to do a lot of analysis. Yeah. But it's a big theta of n. Not too big. We can handle, right? After that, you run a for loop from n down to 2. Yeah. N. Because at the beginning, your element at index n at root. So you start from there. Okay? All right. So you swap a of I and a of 1 and a of I. You put it in place. Okay? Then you reduce the heap size. Okay? Yeah. Then you need to run max heapify to fix it. Fix the max heap. Then you can do the next iteration. Put another element in place. Then fix it, another element in place. At the end, you put all elements in place. Yeah. Okay? Then if you do the analysis, you will see you need this many comparisons. That's big O of n log n. So we get a big O of n log n. Okay? Yeah. The worst case big O of n log n. Okay? Yeah. Yeah. So you can here you can see we achieve all three requirements, right? Yeah. All three requirements. Yeah. All right. Yeah. Yeah. So this part, I want to give you some interesting ideas. Yeah. Interesting. Although I skipped the analysis part. Yeah. But give you some ideas very interesting. Yeah. Yeah. So when you learn these ideas, probably so in the real world situation, sometimes you may need to use the ideas like we learned here, right? Yeah. All right, so let me stop right here. Thursday we will do review. Okay. All right. Yeah. So today the grace period of So if you haven't submit, so today, the end of today, the grace period. Yeah. But regarding the submission, I give you 2 more hours as the cushion, another small grace period. Yeah. 2 hours past the end of today, still no penalty. Okay. Yeah. Yeah. Because sometimes due to some networking things, whatever, yeah. 2 more hours. Yeah. All right. So try your best. Yeah. So then Thursday we will go through this assignment.